Welcome to this audio lecture on strength of material. This course is foundational for understanding how materials respond to forces and deformations in the world of engineering. It is essential knowledge for mechanical, civil, structural, and materials engineers. In this module, we'll begin by exploring the concepts of force equilibrium, stress, and strain, including their representation through free body diagrams. We'll then progress into specific mechanical behaviors, such as the tensile test, biaxial and triaxial stress states, and how materials respond to axial loading, temperature changes, and composite construction. Let's begin. Lecture 1: Force equilibrium and free body diagrams. The starting point of all structural and mechanical analysis is the principle of force equilibrium. In simple terms, an object is in equilibrium when all the forces and moments acting on it are balanced. If the net force and net moment are zero, the object is either at rest or moving with constant velocity. To analyze equilibrium, engineers use free body diagrams. A free body diagram is a simplified illustration of a structure or part of a structure, showing all external forces and moments acting on it. It isolates a body from its surroundings and helps visualize the mechanical environment. Understanding how to draw and interpret these diagrams is crucial for solving problems in structures, machines, and mechanical systems. Lecture 2: The concept of stress and strain. Next, we move into two foundational terms, stress and strain. Stress is a measure of the internal force acting within a material. It occurs in response to external loads and is often discussed in terms of how much force is applied over a given area. Stress helps us understand how materials resist loading and where they are most likely to fail. Strain, on the other hand, is the measure of deformation in the material. When a material is subjected to stress, it changes in shape or length. This change is quantified as strain. Stress and strain are interdependent. When stress is applied, strain occurs. These concepts help in predicting how a material behaves under load, whether it stretches, compresses, bends, or twists. Lecture 3: The tensile test and stress-strain behavior. One of the most common methods used to study material behavior is the tensile test. In this test, a specimen is pulled from both ends until it breaks. This reveals how the material behaves under tension. From the tensile test, we can derive a stress-strain curve which shows how the material deforms with increasing load. Important points on this curve include: elastic limit, where the material will return to its original shape if the load is removed. Yield point, where plastic deformation begins. Ultimate strength, the maximum stress the material can withstand. Fracture point, where the material ultimately breaks. The tensile test also provides data on ductility, toughness, and elastic modulus, all critical for material selection and design. Lecture 4: Biaxial and triaxial states of stress and strain. In real-world applications, materials are rarely subjected to a single type of stress. Instead, they experience biaxial or triaxial stress states. A biaxial stress state occurs when a material experiences stress in two directions, for example, a pressure vessel while experiencing circumferential and longitudinal stress. A triaxial stress state includes stresses along three mutually perpendicular axes, common in soil mechanics, deep-sea applications, or under heavy static load. Understanding these states helps engineers predict material behavior under complex loading conditions. Lecture 5: Axially loaded bars and composite bars. Axial loading occurs when a force is applied along the axis of a component, such as in columns or rods. An axially loaded bar can either be in tension or compression. The response of the bar depends on its length, cross-sectional area, and material properties. Now let's talk about composite bars. These are structural elements made of two or more different materials joined together to work as a single unit. Each material may have different stiffness or thermal expansion rates. The analysis of composite bars involves understanding compatibility of deformation and force equilibrium between the components. These elements are commonly used in bridges, multi-material beams, and even aerospace components where tailored material properties are beneficial. Lecture 6: Temperature stresses and their effects. Materials expand or contract with temperature changes. When this thermal expansion is restrained, say, by rigid support or connections, it causes temperature stresses. For example, a metal pipe constrained at both ends will develop internal stress if the temperature rises and it cannot expand. These stresses can lead to deformation, warping, or even cracking. Temperature stresses are particularly significant in pipelines, bridges, engine components, railway tracks. Engineers must account for temperature variations during design to ensure safety and longevity. Lecture 7: Hoop stress in cylinders and rings. When a thin-walled cylinder or pipe contains internal pressure, such as in boilers or tanks, hoop stress develops. This stress acts circumferentially around the cylinder wall. Hoop stress is a critical consideration in pressure vessel design. If not properly managed, excessive hoop stress can lead to bursting or cracking of the vessel. Similarly, rings under tension or compression exhibit hoop stress, which must be considered in applications like gaskets, tires, or turbine rotors. Hoop stress is essential to understanding how circular components distribute internal forces and is often used in the design of pipelines, hydraulic systems, and rotating machinery. Lecture 8: Introduction to bending moments and shear forces. When a beam is subjected to loads perpendicular to its axis, bending moments and shear forces are generated. A bending moment causes the beam to bend. It varies along the length depending on the type and location of the applied load. A shear force tries to cut the beam across its section. It is responsible for internal sliding between material layers. To analyze beams, we construct shear force diagrams and bending moment diagrams. These graphical tools help visualize how forces and moments vary along the structure, which in turn aids in determining critical points for design and reinforcement. Understanding these diagrams is essential for the design of bridges, frames, building structures, and machinery components. Lecture 9: Torsion and its applications. Torsion refers to the twisting of a structural member due to an applied torque or twisting force. This occurs commonly in shafts, such as those in engines or gear systems. Key concepts related to torsion include angle of twist, how much a member rotates under torque. Torsional shear stress, stress distributed over the cross-section. Power transmission, important in mechanical and automotive applications. Applications of torsion include drive shafts, propeller shafts, and the transmission of rotational power in machines. Designing for torsion requires a good understanding of geometry, material properties, and safety margins. Module 1 Summary. In this first module of Strength of Material, we covered the fundamental principles that govern material behavior under different loading conditions. We discussed force equilibrium and free body diagrams, concept of stress and strain, the tensile test and stress-strain relationships, complex states of stress and strain, behavior of axially loaded and composite bars, thermal stresses, hoop stresses in cylindrical structures, shear force and bending moment analysis, torsion in mechanical systems. These concepts form the basis for advanced analysis, failure prediction, and structural design in engineering applications.